Okay, so welcome Dr. Neda Maleki and welcome everyone. Good afternoon. And sorry for these technical issues that we faced and we had to delay our presentation. Uh, and, welcome Dr. Neda Maleki.
Uh, Thank you, and nice to meet you. And thanks for having me today for lecture on fog computing.
And yeah, we are excited to learn about fog computing and how does it help in terms of IoT. But before start, I just want to get a thumbs up if you can hear us well, because there was some issues. And just let me know if there are any noises, or do you hear us well? Maybe on Discord.
Mm,
I'm just waiting for the. Okay, they said they can hear us, but your sound is a little bit low. But maybe yeah, we can adjust that. So
okay.
today we are going to talk about fog computing, and Dr. Neda is with Lund University, right?
Yes, sure.
Uh,
I can give a short background about me. And
okay, so yeah, you can start.
yeah, yes. Um, I'm happy that I'm supposed to give a lecture on the fog computing, and I'm currently working at the Lund University as a senior researcher, and my work is on modeling and simulation of the data centers energy efficiency using the mathematical modeling and optimization. Um, in my PhD, I've studied my PhD in Iran, and I've working on the optimization of Hadoop, I mean a distributed system and a Spark using optimization model, and
Mhm,
the goal was minimizing the make span of the jobs and maximizing the throughput and uh, mm, optimizing the power consumption.
mhm,
And in my master, I really studied and had hard working on the cloud computing, and I spent a lot of time to learning and teaching the cloud simulator
mhm.
in 2011 when it was a new tool. So I will be happy if I can help and guide a student in this area.
So now you are working in which area at Lund University?
Uh, I'm working in modeling and finding a good model for estimating energy efficiency of the Ericsson data center. I mean,
Mhm.
we are
Okay,
collaborating with Ericsson. Yes,
so you are basically working on the efficiency in cloud computing.
yes, the Ericsson Cloud data center. Exactly. So. I try today to explain and motivate why we need for computing. And after clarification this topic, I will proceed by the what is fog computing and its history and definition and its architecture, the advantages of fog computing and also its challenges. I mean the research area that are very trendy in the academia, and we are working on that. And also some applications in fog computing and the future of fog computing, I mean the market insights.
Mhm.
So why fog computing? Um, we should first see that what is the state of the practice of IoT. I mean, if we look at this picture here, mm, as you can see, all the IoT devices are directly connected to the cloud. And cloud is like a centralized computing paradigm. So these devices communicate with the cloud for getting the processing and computing I mean, processing and computing facilities for doing their work. And this structure is the dominant structure. And we can call it a traditional paradigm. So in the traditional IoT system, devices are directly connected to cloud. I mean, device to cloud communication, and the interfaces are done. In inferences are done in cloud. In cloud analytics. Uh, for understanding why we need for computing, I propose 6 questions. And in each question, I want to consider one parameter. The first one is that the first question is the bandwidth sufficient to push data to the cloud? Um, we want to consider bandwidth. We can see here that in small to mid factories, in per day, they produces a half terabyte of data, and also oil rigs generate half terabyte of data per week. And about the jets, they generate 10 terabyte data per 30 minutes. So, with the digitalization, which means generating more and more data, it will increase by a few factors that really tells us that this huge of data if they want to be sent to the cloud for processing with a 50, for example, 50 megabits bandwidth, it takes the transmission time will be extremely heavy and is somehow impractical. So the idea that the bandwidth is not a problem is not true, and is true only for the applications that they generate a small or the application are very small and they data is small. But for the applications that are big, and it's not true that the bandwidth is not a problem. And the second question is that is a device almost always connected to the cloud? The second parameters is connectivity. So if we look at the rural areas, the connectivity perspective is somehow it's quite different. And all the devices, IoT devices in this area, are searching for the operating that can be connected to it. But why it is true that in the downtown, the devices can have a good and high bandwidth through the 5G and almost everywhere. But if, for example, the farms, if are located here, they need to connect to a high bandwidth. So for also for having the autonomous vehicle for doing the farming works, they might to require to be connected in this environment in everywhere. And so how should we address this problem? And this is the question that we should address. And then number 3 is latency. The question is that would the traditional paradigm be a good option if the application is delay sensitive? Uh, as we know, there are a huge data that's sent from the IoT devices to the cloud, and they are this data to the cloud are being manipulated, analyzed by the softwares, and the conclusion and the result will be back and pushed back to the edge networks. So this is usually fine, but this is very dependent on the type of applications. As you can see that here in this table, for the big data file download or offline backup, the latency that is allowable is 100 second, and it's possible that and it's easy that we can use cloud for its implementation. And also for the YouTube or home automation video surveillance, that the latency is 10 seconds is possible to be implemented by cloud. But about the web search, sensor reading, and interactive website, smart building, and analytics, uh, the latency, which is tolerable, is 1 second, and is somehow challenging with cloud that if we want to implement it. And about the applications like virtual reality, smart transportation, games, and finance, robotics, real-time manufacturing processes, that latency, the allowable latency is 10 milliseconds, is totally impossible with cloud, and it's here that we need really fog computing. So the next question is that how much costs the cloud connectivity, and the cost, we consider the cost criteria here. Cost of connectivity is an issue in smart grids, power distribution system, and the operator has to pay for 2G, 3G, and 4G data links. The next question is, do the companies are comfortable with exposing their data to the cloud? The criteria which is considered here is privacy and security. And they raise in these conditions because all your data is supposed to send to the cloud, and the cloud, all the data are accessible, available to the cloud provider. So some techniques are required that we can keep the data in a local area and don't send them to the cloud. And the last question is that, is it possible sending all massive data generated by IoT to the cloud? And the criteria is scalability. So here we should notice that even if the unlimited resources are provided by the cloud, if it is supposed that the all data are generating by billions of devices by the IoT sent to the cloud, their data, the cloud will be bottleneck. So there is a need of a type of processing platform that we can preserve the data in the area that the data are produced and near the data sources. So what is the solution? The solution is fog computing. Fog computing as an extension of cloud computing and not replacing of cloud computing is the most efficient and logical distribution of computing and storage of data among data sources, IoT devices and sensors, and the cloud. So the traditional paradigm was that IoT devices and sensors sent directly and connected directly to the cloud, but in the by using the fog computing, as you can see in the red box, is possible that the some data are processed near the edge where the devices are placed, and the other data that can be processed later and analyzed later can be sent to the cloud, and they are not real-time data. And how
So before you proceed, Neda, I just wanted to ask this question to you, like maybe for a clarification. Like you mentioned 6 challenges for traditional cloud computing in the context of IoT, or where fog computing might benefit or solve some of those challenges in the context of IoT. So out of those six, like let's say latency, bandwidth, cost, or security, or other aspects. So which aspect do you think that fog computing solved or benefited most?
Of course, I will mention it in the next slide. For example, that when I want to talk about the perks of the fog computing, which one of them is reliability.
Mhm.
Instead of this, I bring here the most important things. So, of course, it can solve other problems and we can benefit it. I will later. I will explain it.
Okay.
Okay. So the fog nodes closest to the network edge ingest the data from IoT devices, and then, and this is crucial, that the fog IoT application directs different types of data to the optimal place for analysis. For example, in this picture, you can see that we cannot run everything in the cloud. There are latency, mobility, geographic focus, and the network bandwidth, reliability, security, and privacy challenges that should be addressed in the cloud level. And of course, at the same, it is the same that we cannot run everything in endpoints. I mean, the edge devices, because there are some problems like energy, the battery of the devices are limited, and the space, capacity, environmental reliability, modularity, and security challenges. So you can see that using the fog computing and with the layer of the fog nodes here, applications can be partitioned to run at the optimal network level. And for the IoT, I mean the edge level, the geographic coverage is very local. For example, in a city block, and data storage duration is transient. Response time is milliseconds to subseconds.
So also from this solution, or from for this paradigm, I mean, how should we look at fog nodes, or what are those fog nodes? Can you like briefly uh, define fog
Of
nodes?
course, the fog nodes are consist of the servers,
Mhm.
routers, switches, and actually the fog computing is the processing and the inferences are done in a LAN. I mean, local area
Okay.
network. So it consists a lot of devices, as I
Mhm.
mentioned, servers, switch, and routers. And this is the difference between the edge computing and the fog computing, where the inferences and the processing is happen is
Mhm.
the key difference. In the fog compute, in the edge computing, the inferences are is happen in the devices, while the inferences in the fog computing is happen in the in the fog nodes. Okay.
Mhm. So by inference, you mean any kinds of analysis or prediction or whatever?
Yes, exactly. Yes, any kind of yes, we can do, for example, ML or deep learning also.
Mhm.
And so what's happened? Sorry. And the geographic coverage for the cloud is global, and data storage duration is months to year, and the response time is minutes, days, or weeks. So, what is fog computing? Until now, I didn't talk about it much, but I want to say something, some history about it. In 2012, Cisco, which recorded the name Cisco fog computing, means that when the clouds are high in the atmosphere and the fog are near the ground, near the users, is synonymous with the term fog computing, which means providing the computer and storage facilities near to the end user. And an open fog consortium was set up in 2015 with founding members ARM, Cisco, Dell, Intel, Microsoft, and Princeton University, and additional participating members, including Hitachi and Foxconn. And the loosely aligned and largely synonymous concept like edge computing was introduced by IBM. I'm not sure in which year it was proposed because I didn't find also in the Wikipedia when it was proposed. So
Well, the edge computing was it proposed to overcome some of the challenges by fog computing, or why the edge computing was introduced?
Uh, as I understood it, the edge computing, which means the processing in the devices near the users, it was existed before, you
Hmm.
know. For connecting this server, these devices to the server of the cloud, the fog computing is proposed. So I think that the edge computing is has proposed before
Okay.
fog computing. Yes. So what is fog computing and definition of the fog computing is that it's a decentralized computer architecture that processes and preserves information between the source of origin and the sources and the resources of the cloud. And fog computing contributes to the minimization of overhead data transfer and ultimately increases computational efficiency on cloud networks by reducing the need to process and retain vast quantities of superfluous data. The fog computing paradigm is primarily driven by a continuous rise in Internet of Things devices, where an ever-growing amount of data is generated from an ever-expanding array of devices in terms of volume, variety, and velocity, which is called 3Vs.
But there are now more Vs, right? There are, I think, five Vs or six Vs now.
Yes, they are. I can tell you 16 to 17 Vs, but
Hmm.
I bring it veracity. You can say yes. There are more than 3Vs. I bring the most important one,
Okay.
and yeah. And data processing in cloud versus fog is like this picture. You can see that before, when the IoT device sent its data to the cloud, it's like that. It was like that human eating pattern when we bring the food, which is mean data, to our mouth for eating, and the processing here is eating. But nowadays in fog, it's like animal eating pattern, which means that an animal brings his snout or beer next near to the food and eat it. So the things is moved in the network. It's the processing, not the data.
Hmm.
And cloud computing operates on big data, while edge computing operates on instance data, that is a real-time data generated by sensor or users.
So in this figure, so there can be multiple layers of fog node between the source and the cloud, or
Exactly,
usually.
yes. We can have multiple fog nodes, and each fog node can have is a separate network that manage some related IoT devices,
Hmm.
and is responsible for that devices. And as I said, it's a decentralized, it's a distributed processing, and each group of IoT devices can have fog node, and they can push the data there, and it can be hierarchical.
Hmm.
Okay. And for computer architecture, I want to talk about it. The fog network is the bridge between the data collected from sources and the cloud. This computing that provides real-time interaction is a distributed network environment that is closely related to the Internet of Things. The fog architecture owes its rise in demand to the need for distributed data storage and processing facilities, as this could not be performed by cloud computing, an alternative. Uh, in other words, fog computing architecture is used. The fog network is commonly known as a decentralized and flexible computing structure, as it provides ample resources, sufficient resources, and the data associated with it to enhance its performance and provide efficient results to the cloud. Fogging, fog network, and fog computing are used. These terms we can use all of them. Fogging allows decision making and computing through IoT devices and ensures only relevant data is sent to the cloud, as I mentioned before. And fog computing architecture consists vastly of the physical and logical elements of the network, including the hardware and software, and this establishes a large number of interconnecting devices. For computer architecture contains multiple layers that I will explain in the next slide. These layers consist of many networking devices such as routers, set-top boxes, proxy server, base station, etc. And these levels are assigned various tasks to be conducted on the given data.
And these devices, they are the real physical devices. They are not virtual devices, right?
Yes, exactly. So the first model is a hierarchical architecture model. Um, we can see in the edge devices layer, there are cell phones, cameras, smart cards, readers, and this device can detect and collect data. The second layer is we mean by nodes, routers, gateways, entry points, base station, individual focus servers, and these nodes supply the end devices with facilities. It can also temporarily compute, transmit, and store the data. And the top level is the computers that can provide high performance with massive storage and machines, servers, and permanently save data for backup and remains persistent user control.
So, for example, if in this figure, if I think uh, a fog node as a gateway, for example, so the devices or edge devices, are they connected to a dedicated fog node, or they can change or the fog nodes?
We can configure it because there is a topic in this there for computing it's a task offloading, because if a gateway cannot respond, it's not responsive, so we can offload the task from
Mm-hmm.
the IoT devices to other fog nodes.
Okay.
Yeah, and so the second model is layered architecture. You can see that in the physical and virtualization layer, this layer consists of physical and virtual nodes as well as sensors. The sensors are distributed geographically to sense the environment and retrieve data. This monitoring layer the receive nodes and sensor will be monitored thoroughly. At what time and where the fog node performed the tasks will be observed. Another key feature that will be monitored is the energy consumption of the nodes.
Mm-hmm.
And the pre-processing layer collects, analyzes, and trims data to get meaningful insights, and after which the data is stored securely. In the temporary storage layer, that is exactly where the pre-processed data will be stored. Here, performance elevating activities such as data distribution, replication, deduplication, and virtualization of storage spaces are performed. And in the security layer, The data received is sent for processing, encryption, and decryption. It also ensures privacy and integrity measures are followed religiously. This layer also makes certain that the data isn't tampered with.
Hmm.
And in the transport layer, the word shows that the data should be sent to the cloud. And this layer receives the information, and this main objective is to upload the pre-processed secure data to the cloud. And this is the final stage of the layer for computing
So,
architecture. That
so for this architecture, you said it's a layered fog architecture, but
yes.
does it implies uh, for each node, fog node, or some parts, some layers of this architecture correspond to a fog node? Because it also includes sensors and things and wireless sensor networks and so on.
You mean you mean in each layer we have the sensor network? What is the
Now, for example, you have six layers here, right?
yes,
And the bottom layer is the sensor layer or things
yes,
layer. But in your fog node, you usually don't have sensors or device or things layer, right? You have like
yes. I got it. Yes, it's a It's shows the total from the device. I mean the edge to the cloud.
okay,
Yes, that is connected from the sensors, wireless sensor network. That is the edge. The edge devices placed here, and we have the monitoring and pre-processing layer, temporary storage and security layer in each fog nodes when we are start
okay,
from bottom to the cloud. Yes.
okay. So it doesn't include the actual devices or actual sensors.
Yeah.
It's only the connect network or the connectivity from the
It,
sensors
yes, exactly.
until the cloud. Yeah.
Yes. So I wanna tell you some perks of fog computing. They are as follows: enhance user experience because as data is analyzed locally and then transmitted to the cloud, there are fewer technical errors and provides instant responses, which will in turn increase the satisfaction amongst users and conserve network bandwidth. We talked about it. Many data analytics tasks, even critical analysis, do not demand the scale that cloud-based storage and processing offers. Meanwhile, connected devices constantly generate more data for analysis, and for computing eliminates the need to transport most of this voluminous data, I mean huge data, saving bandwidth for other mission critical tasks. Instead of providing large sums of unfiltered data, this computing architecture method transmits only accurate and necessary data to the cloud source. And it improves response time. I mean, it minimizes latency. Real-time applications will benefit largely from live and instant responses. This is because the fog nodes are placed remotely around the data source, and also because there are minimal shutdown and system failures in the network. And security and data privacy is other benefit by proposed by the fog computing. It handles the data process in the network with the ultimate security features and also ensures all sensitive data is withheld and processed locally. This ensures that no data is tampered with or misused. This is done by protecting the fog nodes through policies and controls established amongst the networks, and it also reduces the operating cost because processing as much data locally as possible and conserving network bandwidth means lower operating cost. And it improves reliability because IoT devices are often deployed under difficult environmental conditions, and in times of emergencies conditions can be harsh. For computing can improve reliability under these conditions, reducing the data transmission burden and deepen inside without sacrificing privacy. Instead of risking a data breach, sending sensitive data to the cloud for analysis, we can analyze it locally to the devices that collect, analyze, and store that data. This is why the nature of data security and privacy in fog computing offers smarter options for more sensitive data. And it boosts business agility only by knowing that resources customers need, what resources customer need, where they need those resources, and when the support is needed, can businesses respond to consumer demand quickly. Fog computing allows developers to develop fog applications rapidly and deploy them as needed. Fog computing technology allows users to offer more specific services and solutions to their customers and locate data and data tools where they are best processed, and all based on existing computing capabilities and infrastructures.
Sorry,
There are
you
some
also mentioned that fog computing handles well or supports the scalability problem. So did I forgot or did I not catch how fog computing supports the scalability? Correct.
The scalability, you mean how much scalable is it? You mean?
In scalability in terms of, let's say, processing or big data or large scale data.
Of course, it can handle the big data because in the big data, as I show you in the previous slides, some decision are important that it be made in the real time. So if the data, if the some part of the application is really should be done in a real time, so we can
Mhm.
use the this fog computing for that, that enables us to process the data near the edge. But the some of the task, the some part of the application, I mean the other task can be done in the kilo. So how much the data we have a also we have a topic that means data management. I mean, it's how much your data is, how what the size that should be done with the full computing.
Mhm.
So uh, we can handle this the huge data also. I mean, the big data using collaborating these three layers, and
Mhm.
it makes our solution scalable.
Mhm. So I guess you also have some applications later on to see in which
Yes,
kind of scenarios what fog computing is more useful.
yes, I show the application they are using these days. Yeah.
Mhm.
And there are some challenges of fog computing. The research area, if students like to work in this area, they are the hot trendy topics. Fog nodes configuration, I mean sensors, networking, cloudlets, base station, vehicles. You can you should know that in a LAN, I mean local area connection, that these nodes, they are all called they are all called nodes, are used. How we should configure them, and in the nodal collaboration. Three types of collaboration between the nodes. It can be cluster, peer-to-peer, or master-slave. And I will show in the next slide what they are. And the resource service provisioning metrics. What are the metrics that when we want to provision and get the resource to the users? Time, data, cost, context, and energy and carbon footprint are the most important of them. And the service level objective, latency management, cost management, network management, computation, application, data, and power management. They are the hot topics, and each area has we can do a lot of research on that. An applicable networking system means that in which networks we can apply the fog computing. In IoT, as we can see, and I explain it, IoT devices are connected to the fog nodes, and fog nodes send and receive the data to the cloud and to these nodes. And in the mobile network, I mean radio access network, and in cellular networks, in content delivery networks, all in this area for computing can be used. And always the security concern we have in the these networks topics. So the authentication, encryption, privacy, and those attack can be considered. So as you can see in this picture, I said there are cluster. There, these red circles are the IoT devices that they can form a cluster with each other, and they are connected finally to the base station. And this they are the fog nodes. You can see each cluster has its fog nodes, and finally they are connected to the base station. And this from base station it will send to the cloud. And in the master slave, that there is a node is called master, and there are some nodes they are called workers, agents, or clients, and they are collaborating through a master node. And in the master node, we don't have any real data, and only the metadata of these clients are stored, and they can be two. The master node can have how can I say, a backup node. If it fails, we can use the backup. And in the peer-to-peer, the connection, the communication is in pairwise. I mean, two by two, the nodes are connecting to each other. And I bring I try to bring some details here, and if someone is interested, can see um, these topics. And so there are very interesting, and my area is this computing management. Resource prediction, resource allocation, resource coordination. Okay. And some for computing applications are linked vehicles, and smart grids, smart cities, and smart buildings, and real-time analytics, and smart transportation, agriculture, a smart factory and manufacturing, and connected healthcare. In the link vehicles, self-driven vehicles are now available on the market, producing a significant volume of data. The information has to be easily interpreted and processed based on the information presented, such as traffic, driving conditions, environment, etc. All this information is processed quickly with the aid of the fog computing. And in the smart grids, which means a power distribution system, and smart cities, the energy networks use real-time data for the efficient management of systems. It's necessary to process the remote data near to the location where it is produced. It's also likely that data from multiple sensors will be produced. For computing is constructed in such a manner that all the problems can be sorted. And real-time analytics data can be transferred using for computing deployments from the location where it is produced to different locations. And for computing is used for real-time analytics that passes data to financial institutions that use real-time data from production networks. And you can see here transportation. For example, what data is critical from a moving vehicle? How do you respond to data that is literally in motion? It moves. How do they work together? And in agriculture, how much data does a cow generate, or a field of crops, or does all of the data need to go back up to the cloud, or like the manufacturing and entrepreneurs, some questions are raised. And future of fog computing in terms of profit, according to PR News Wire, the fog computing market is set to reach 539.8 million by the year 2026. Uh, and it was in 2090 $40 million, and this clearly shows the tremendous growth opportunities that this domain has to offer. And for computing market scope and market size, the increase in the adoption of smart devices among population across the globe is escalating the growth of fog computing market, and the fog computing market is segmented on the basis of computing solution and application, and the market scope and market size are divided into on basis of the computation in terms of hardware and software. Hardware are the routers, and software are the designing platform applications. And uh, and the top sorry, and the top key players in the fog computing industry are the ARM Holdings, Cisco Systems, Cradle Point, Dell, Foghorn System, and Fujisto. And you can see the key players in the fog computing.
So these key players, I guess some of the key players are also like who started this fog computing paradigm. But then, for example, for Cisco, they are providing cloud computing platforms as well as they are also providing fog computing platforms.
Of course.
So
Uh,
for fog computing platforms, I mean, what they are providing as a devices, or just to get the idea, or just to
yes, the name of their Cisco for fog computing platform is Kenitech.
okay.
Yes, and they are using this for computing, and also for the I don't know if I bring the um, Fog OS here. Yes, it's belonging to one of these key players, and they designed also their for computing devices.
Mhm. So basically, if I want to use for computing, I have to buy one of those platforms and then set up in my premise.
Yes, they of course. Um, you mean the compatibility of the devices? If they design some for computing devices, if it is working other
Well, for example,
platforms.
if I just want to use for computing, so what should I do? What should I do? So I should buy those one of those six Cisco system for
Yes, it's
computing device and then just connect it to the cloud.
okay. This one can have is for computing, but finally you should provide it from one of this company. Uh, and I think that for setup for computing, of course you should use these devices.
Hmm.
And as the Cisco is pioneer, so it would be beneficiary to use this device.
Hmm.
And the other there is a graph here that shows how for computing is usage of for computing is increasing in the years from 2020 to 2027. Uh, there are five regions: North America, South America, Europe, Asia Pacific, and Middle East and Africa. In North America dominates the fog computing market because to the rise of the I mean, because to the rise of the investment in the hard in the research and development, I mean R&D in the fog computing, and also the presence of the prominent industry in the North America, and the high adoption of the IoT in these regions. And you can see that in North America, also in this graph, all are using this, are increasing, but North America is pioneer. And about the what was it? The Asia Pacific is um, uh, I mean is witnesses the highest CAGR, I mean compound annual growth rate
Mhm.
during the forecast from 2020 to 2027. And because this is because of the government support and the growth of the connected cars and by adoption of the cloud services in the developing nations. So there are some other reported about it, and it was interesting. So I bring some of them here, and now it's time for the demo using iFog simulator. Let me tell you some introduction about the iFog sim. iFog sim enables modeling and simulation of fog computing environments and is used for evaluation the resource management and scheduling policies across edge, fog, and cloud resources under different scenarios. And iFoxim is provided by Clouds Lab, the University of Melbourne. This is the link for you can study here. And this is the GitHub link for getting the source code of the iFoxim and for, for using and extending your idea, your algorithm, or any proposal you have. And the source of learning is in this paper, and it's called iFoxim Toolkit for Modeling and Simulation of Resource Management Techniques in the Internet of Things, Edge, and Fog Computing Environments. And there are two case study. One of them is a latency sensitive online game. So if I want to show the demo, there are the references, and thank you for your attention. But I want to show you the, let me open the, okay, should be launch. It takes sometimes. As I restarted my computer, all the applications was
So basically, you started with this open source simulator, and then you extended it for some use cases or some simulation.
yes, yes, you can implement your algorithm, your idea about how to improve the resource allocation and resource management from the edge to the cloud, and using this open source. It's Java based,
Mhm.
and you can see it's an extension of Kelosim, but only iFoxim you can download from the GitHub, and when you download it, it's you can see some iFoxim master,
Mhm.
and there are some folders means jar output result, and in the source folder, if we come here, there is performance evaluation, perf eval, and there are some example for learning, and one of them is VR game fog. Let me tell you what is this. Okay, page 10. And yes, the latency sensitive online game is a human versus human game. Um, it involves augmented brain computer interaction, and to play this EEG tractor beam game, each player needs to wear a Mindo, I mean it's from Mindo Force S wireless EEG headset that is connected to his smartphone, and the games runs as an Android application on a user's smartphone, and the application performs real-time processing of the EEG signal sensed by the EEG headset and calculates the brain state of the user. It's like the sleep tracking. I don't know if you know, they can track your sleepy if you sleep very deep, or no, you don't sleep very well, and because from the alpha and beta tracking they can understand it. So it is the application, and they have implemented it here. I can show you. You can see we can define fog devices, we can define sensors, actuators, and a number of departments. I mean, in each department can have its fog nodes, and number of mobile per departments, and EEG transmission time. And okay, from here the simulation is starting, and so we can come here. They are, for example, you can define your fog devices. Oh, sorry, here. It's extended from power data center, which is in a cloud sim, and foggy device is a kind of host. So it has uplink bandwidth, downlink bandwidth, and uplink latency, and energy consumption, and so you can define all this here, and rate per MIPS, total cost, as you can see here. And if I want to run it, first let me show you. You can define all other the nodes, okay, not just fog devices, all sensors, actuator. Yes, you can define all of them. And if I want to run it to see what would be the result, this is like
Okay, so while it's running, so there was a question on power consumption. So does a project utilizing fog computing has a significantly increased power consumption compared to the cloud project?
yes, if we want to implement our algorithm having the comparison, of course uh, it will work when we use fog nodes, and the power consumption will be less.
So it's
As
not,
you can see,
it will not increase, it will decrease basically.
sorry, yes, it will decrease. Yeah, and as you can see, energy consumed by the cloud, it's yeah, it's too much, and and total network usage, and the cost of and they are the device 0, device 1, device 2, and it's hierarchical. And I can show you, and you can also have the other metrics like execution time and the CPU execution delay and the other things, and you can write your code also for calculating the things you want, the measurement. And if I want to show you the GUI, I should let me see if it is yes. And there is I can show you if we want. We can both define our topology and also use the default topology is defined here. If the fog GUI is come up, I can show you. It's
I
some
guess it's still building the
how
workspace.
building building here. Sorry.
I guess it's still building the workspace, so it's taking some time.
Um, yes, maybe 50% of. Oh, it was so fast. I don't know what happening. Okay, sorry for the. Mm, what's
Yeah,
happening?
maybe it's a long, very, very large repository.
Yes, of course it is. And okay, I can show in the meanwhile the properties, router topology. You can see it's a JSON file that nodes, for example, it can be anything, switch, router, and server for node, and name. You can see the name and then actuator type and the type and the rate permits and download bandwidths and upload bandwidths and the RAM size of the RAMs, for example, 1024
So you are
megabytes.
basically configuring each fog node in this JSON.
Yes, we can configure it, but you can see that we can configure it using GUI, not by hand. Also, we can write
Yeah.
it. Yeah, here. It's a topology creator. As you can see, we can add sensor. For example, sensor one, or I don't know how many sensors you need, and you can uh, have a distribution of deployment. It's normal distributed, uniform distributed, and deterministic distributed. And it's mean and standard deviation, minimum, maximum, and like this. We should it's mandatory fields. So let me bring from the application. It takes two time if I want to determine all the higher level of the and level of the fog. You can add an actuator with the name and type, and you can add the fog device. For example, you have fog device in the middle, and you can also define the cloud data center. Okay, it consists. It can be any type of this server processing. And the level, it means in the topology, it's in level 1 or level 2 or level 3, and upload link, download link, and the capacity in terms of processing, capacity in terms of RAM, and also the MIPS rate. And the other things is the add link. When you define here, you can add some link from the sensor to the other sensor here with the latency, for example 50 seconds. This is for bringing. Let me bring some topology from here. It's see. In C. Okay, I forget. Let me no C and users and here. Mm, in the project Gits, I have iFoxim, and in the iFoxim, we have topologies. We can okay. If this is the topology defined for the VR game, we can you can see if I wanted to put using this, it takes it will be like this, and this is a topology file we can define, and we can save it in anywhere we want, and then exit. So I hope this very short introduction will be useful, and this is finished.
So for the GUI,
Okay.
did they use JavaFX? So there was a programming related question, or which?
Sorry, I didn't get your
So
question.
for developing the GUI, which API or libraries they used? Is it JavaFX
For developing, yes,
for
for
the GUI?
developing this for GUI, you mean? Yeah.
Yeah, the
This is
GUI
the
that you
swing,
showed.
Java swing. Java swing is used.
Okay.
Yes, and you can see JFrame. They are from the. I can show you. They are all from the event listener, action listener.
No, it's fine.
They
I
are
mean,
from Java Swing.
there was a question about this, so it's fine. Yeah.
Okay, and also what else? It's that can be okay. You can put your placement, for example, placement algorithm here. Um, there are some I mean placement algorithm. One of them is module placement only cloud, module placement mapping, module placement edge bar, and module.
Yeah, I think those details will not be interesting for the students, but
Okay.
there was a similar question that I already asked. So uh, about the question on fog node. So is fog node a virtual computer, and does it act like a filter or converter before the data is sent to the cloud? So is the
Yes,
fog a
exactly.
virtual
We
computer or
mean
it's a physical computer?
we mean by filtering the data that some of the data are not required to send to the cloud. So the processing of and storage of the data can be done in these routers and switch. This is true that we say that it is filtering. Yes.
So, but is fog node is a virtual computer or a physical computer, actual physical machine?
Yes, it is a actual computer, and it can be virtualized as we can use the virtual machine on that.
Hmm.
It They can be virtualized.
Yeah, I hope
I'm
uh,
Yes,
who asked the question is answered. So
I hope also. If I don't know if he or she gets his answer or
yeah, so I think you are done with your presentation, right?
okay. And many thanks for inviting and having me here.
Yeah, thank you also for this presentation with many information and lots of new concepts.
Yes,
But
sure. I hope it will be enjoyable for following the topics, and I will be happy to answer any
yeah,
question.
feel free to ask your questions before we close the session. But I would also mention that you already met Neda on our Slow TV day because she was here visiting our campus. And right now, Neda is part of Lund University, but soon she will be our colleague. So she will be starting doing her research on IoT and applied IoT in Linnaeus University, right?
Yes, of course.
So she is going to move to Kalmar probably soon.
Yes, and 2 months, I think 2 months. Yes, in the 1st of October.
Okay. And I guess I already am asked a lot of questions during your presentations that students did not ask that many. But if you have any other questions, you can always tag Neda on Discord because she is also on Discord. So
Sure.
she can directly answer your questions. And with these words, I would like to thank you, Neda, again for the
Thanks.
presentation and for the time with us.
No problem.
And have a nice evening, everyone, and have a nice evening, Neda.
Everyone, bye. And thanks for listening.
Yes, bye bye.
Bye.